Welcome this afternoon with my talk, Locating All the Things, or Locate All the Things. I'm Derick. Yeah, I won't get much into that. But what I'm talking about today is started out as a story from another conference, actually, where I'd be out after conference, conference social ran out, and we wanted to go to the pub. But I live in London, and London pubs are very difficult to find open anything on after 11 p.m. on any day of the week, really. So we wandered around a little bit and just couldn't find anything. So I thought, well, maybe I can do something about it, right? Because there's so many pubs in London, there must be some data, and there must be some way of figuring out which ones are still open. So what I started working on, and I never got actually to the point where I wrote a website to find pubs that are open at a certain time of the day, but what I went into is looking at some data, seeing what I could do with that, and then figuring out where those places are, depending on specific criteria. So basically to try to find open pubs. So the data that I'm using in this presentation is OpenStreetMap data. Have any of you used OpenStreetMap data? Have you used the data or have you used the tiles? Both? Anything else? Shouting out? No? Okay, there's lots of hands, but no shouting. All right, so just to explain what OpenStreetMap is a little bit, it's in a simple term explained as it's a Wikipedia for maps. The idea of it is that lots of people, volunteers, add data that describes how the world looks like. That includes streets, parks, buildings, points of interest, post boxes if you're inclined, bike parking, tram lines, anything you can think of, as long as you can verify it as something to be on the ground. So basically any of you should be able to go out and figure out those things and add them to the map. It's important that the data that is added to OpenStreetMap is free from any other copyright infringement. So that means you can't copy anything from Google Maps or from any of your national mapping agencies most of the time. Although in the Netherlands that is a bit different than it is in the UK, where there's no open data for this whatsoever. Whereas at least in the Netherlands, most of the building data is at least available through an open license. But it's important that the users of this data can make use of the data, not only of how it looks like, but make use of the data underneath that to do their own things, and that is always under an open license. So as I said, it's sort of a Wikipedia for map data. And it's a lot of work. So this being geographical data, let's have a look at how this actually looks like when you download this. And what I'm focusing more on is what kind of data items you have in there. So if you download OpenStreetMap data, it usually comes in a very big XML file. Where very big is a number from, well, I'll get to that in a moment, how big those things get. And what it stores in there is, first of all, a collection of nodes. And nodes are basically points on the ground. As you can see, the node, the example I have at the top here, it has an ID number, it has a latitude and a longitude. I don't know where this is, but it looks like somewhere in the Netherlands, maybe. I don't know. Belgium? I think it's Belgium. We can try that out later. So yeah, that's the point, and that's what it describes, right? And there's no other data, important data attached to it, except that, of course, OpenStreetMap registers which user added it and when, and with user ID and a version number, and in which commit change set number. Of course, just recording points is not very helpful when you want to store roads or buildings, right? So a road is usually a collection of points. And the type that is used for this in OpenStreetMap is called a way. And ways, again, have IDs, against user and user IDs attached with it. And then they have a list of references to nodes. Those references don't include the latitude and longitude anymore, meaning that if you want to figure out where on the ground a way is, you need to first look up all the locations of all the nodes. And then as a third item is something called tags. And a tag is a description of either a node, a way, or a relation, but well, ignoring the relations for now. And that basically describes what this object is. So in this case, it is 4 tags that I have here. We have a house number, a street name, what it is, in this case a pub, and what the name of this pub is, which is the North London Tavern. So yeah, those are the ways how you describe specific objects. And they sit as sub-elements inside the ways or nodes. Like where you have the NDs for node reference, you would also have extra tags in there to describe the elements. Now, tags in OpenStreetMap is something that are not defined by default. best to explain this is that there's a common set of tags that people use, like what the address is, or what the type is of what the website address is of a specific point of interest, or that it is a shop, or that it's a highway or a tertiary way, and things like that. All those tags are fixed tags that everybody has agreed on to using, so that things can be written to process the data and render a nice map out of it, right? That makes sense. But it is also possible to add your own tags for whatever you want. It's difficult to see in the tag cloud here, but there's one that says payment cash, whether a point of interest, like a shop, accepts cash as a payment, for example, or whether there's wheelchair accessibility, or whether a shop sells Marmite, things like that, right? Yeah, those really crazy things show up in the data. So, or some Germans have been mapping which hours of the day there's sun on specific benches in parks, kind of stuff. Yeah. Anybody with a special interest can add their own tags if they really want to. And there's many different things. There's people that have used it for skiing resorts, or for maritime points and things like that. So there's lots of different special interest groups. Or rail geeks add lots of information to railways and stuff like that. So the interesting thing is that because it is so distinct of a set of data that you can have, it actually makes sense to at least have a data model that can store this stuff as well, right? So that's the first thing I want to talk about before I move on to the geolocation aspect of it. So how does tagging features work? Well, you take a photo of a place, then in there we find a pub, which is a Chandos. So we record, well, how many levels does it have, what the house number is, what is the building, the name. In this case, it doesn't have a phone number and stuff like that, or an opening hours. But sometimes they do. There's also other things in, like there's like a little cafe there. This has the website mapped, for example, and so on and so on. So when you look at the data on OpenStreetMap, if you go to a URL like this, you get information, you get the tags that belong to this object. So in this case, this is a street not very far from where I live. It says, well, highway secondary, it's a secondary road. The name of this Bronsbury Road, and the reference number is B451. That's just the name of the number of the road. And then also sometimes what the sources of those numbers are. And there's different ways how you can store this data. I'm using MongoDB here because I first thought that would be a great way of actually storing this data, because as a document store, it doesn't particularly care which fields a specific document have, just like tags are not necessarily described for each OpenStreetMap object, right? So it seemed like a good way of doing it. Also, I like playing around with MongoDB. To be fair, I work for them, but that has nothing to do with this presentation, because I wrote this way before I started working for them. But so yeah, the way how you store data in MongoDB is you store documents, as we call them, in a collection. And they're equivalent to having a record in a table in a relational database. With the difference is that the fields in each of those documents don't have to be always the same. So in a collection, you can have multiple documents where the fields are something else, right? Except for the underscore default, which is your unique key. So that's what I've done here, right? I've taken the tags that were associated with this OpenStreetMap object, the road in this case, and I've transcribed them to this JSON document where you have the field names and the field values. So the underscore default is now the W, stands for way, and then the way number. And then we have the tags highway, name, ref, and source ref, where I changed the colon to an underscore, because that's easier when using PHP arrays and programming and stuff like that. So that's one way of storing it. But what MongoDB also supports is storing data in slightly more richer data sets, or richer data types. So instead of having just top-level fields, you can also create something we call nested documents sometimes, where in this case the field tags then has all the tags that are available on this object, but then stored in a subdocument. And the fields, you can access those fields directly by using the dot operator. So you can do a query that says, find me all the documents where tags.highway equals secondary, to find all your secondary roads, for example. So the data model is a bit richer, because you can store arrays, and in this case we do this nested documents. Now, querying, as I said, can be done by running some queries against the database. So the way how this looks like on a MongoDB shell is as follows. So the MongoDB shell runs JavaScript, and the reference DB is the current database you're connected to. So what basically this query says that we're using the current database, and we're using the POI collection, and on that we call the find method, And then the query that we have, it is not, as you can see, SQL here, but it is sort of, you give an example document of what you want the documents that you want to look for look like. So in this case, it basically says, find me all the documents where tags.highway equals secondary. Now, there's a few other things that the query language in MongoDB does, is because you can also look for fields that don't exist or fields that exist. Unlike a relational database, of course, where the fields always exist, you can't query on it, right? You can query for null values sometimes, but in MongoDB, those null values, just the fields don't exist because you don't have to store them. So, for example, to find all the documents where there's a field that is called tags.highway exists, you can construct a query like this. So instead of doing equality match that we do in the first one here, where we try to match tags.highway with secondary, we now use a slightly more interesting query operator, which is called exists, and we match that to true. But basically, that query says, find me all the documents where there's a field that is called tags.highway to find all the roads in a data set. Just like relational databases, indexes are also very important in a non-relational database like MongoDB. So to find all the pubs, we can look for all the documents where tags.amenity, which is OpenStreetMap slang for something where you can do things, equals a pub. And when you look at the explain output, that tells you basically how the query planner looks like. An important thing to see here is what sort of state you get. And I won't go in detail on all the other things that you see, but this is the important one. Col scan stands for collection scan, which is MongoDB speak for a table scan. That is, of course, something you don't want to do if you have 5 million documents in your database, right? Because it's going to take a long time. So what do you do with this? You can probably guess is that you create an index on that. So that's what I've done in the first line on the MongoDB shell. We create an index, and then when we run the explain again, we now see instead of col scan, we see ix scan, which stands for index scan. And that is, of course, what you want to have, right? So in order to find all the pubs, I had to create this index, right? Create an index on tags.amenity. So that's what I've done here. But if we want to find all the highways or match highway names, then we need to create an index on tags.highway. And if we want to find rows by reference number, we have to create an index on a reference number. You can probably see where this is going, right? For any tag that we want to look up documents for, we have to create an index. And of course, that is not a particularly good way of doing it, because, as I said before, it is impossible to know which tags exist up front, because users can define their own tags. And of course, you also hit index limits or other limits, like you can only have 64 indexes per collection in MongoDB. Or, of course, the more indexes you have, the more time it takes to actually insert documents, because more indexes have to be updated, right? There's no difference there with a relational database where you have exactly the same problems. So, so there's one way of storing this data that I've already done, and now switch to PHP syntax that makes it a bit easier to see, although it is very similar to what you see in JavaScript or in JSON syntax, where we can do the queries, for example, find all the roads that are called Strand. There's a road in London somewhere with matching tags.name to Strand. And then to find all the roads, we can do tags.highway and making sure that it exists. And instead of true, I've used one here, but you can use true too. So, as I said, lots of indexes have to be used for this, and an index cannot even be used for the exist query. So you're going to have to create more indexes for that as well. So that doesn't work very well. But it's very easy to extract data from, right? Because if you see a document, you have all the tags, because they're key value combinations. But in my case, that didn't work, because I wanted to look up documents by almost any tag, and then this doesn't work because it gets very slow. So what I came up with as another way, which is a bit of a hack, but it does solve the problem quite well, is where instead of having key value pairs as a nested document, what I've actually done is I created an array called tags. And in this array, I have concatenated the key value pairs from OpenStreetMap tags into a string. Now, if you create an index on tags in this case, because tags is an array, MongoDB actually indexes every single element in this array as a specific key, meaning that if you do a simple query like we match tags to name equals strand, it can still make use of the index, even though it's an array of values, which is a really handy way of finding this kind of stuff. What you can also do is do things like queries. In MongoDB, we use regular expressions for these. So you can actually construct a query where we match against all the tags that start with highway equals to find all the documents that have roads, for example. And for each of those cases, you can actually use the same index. So that means you only need one index for all the queries that you can ever think of. Of course, you now end up with a slightly more hacky way of reading the data because you have to loop over this array of strings and then split it out on the first equal sign. In case somebody had thought to create an OpenStreetMap tag with an equal sign in it, this of course is also going to fail. But then again, yeah, that is basically shitty data in the database, and you can just ignore that because, well, whatever. And there's quite a lot of bad data in OpenStreetMap as well. But it is a good enough solution to find all the documents that I want based on the keys. So with this, I can now find all the pubs by matching where tags equals name equal, where tags matches amenity equals pub, for example. So I get to find all my pubs, but it still doesn't solve me the problem of finding them where they actually are. So this is where the locations come into play, right? So this is a screenshot of my mobile phone app where I take notes on the map. And all the orange things are things I haven't actually put in OpenStreetMap yet. As you can see, I have a whole lot of work to do still. All right, so how can you store location information? Well, because we're storing this in MongoDB, it also needs to be in the same JSON-like format, right? And luckily, there's a standard for storing geospatial information inside of JSON, which is something called GeoJSON. And it's a format for encoding a variety of geographic data structures. So you can store points, or line strings, or polygons, or multi-polygons, or collections of objects. And this is a standard that is used by quite a lot of other things, or by some HTML APIs. So OpenLayers is a way of rendering data on top of a map. Leaflets, which is something that I've been using in the examples I'll be showing you there. But there's also like PostGIS can also read GeoJSON. And as I said, there's a whole bunch of different types that we have here. So we have point, the multi-point, a collection of points, strings, multi-line strings, which we use for ways, polygons, which we use for buildings and parks, for example. And then you have something called a geometry collection, which basically can array of any of those data types that I've mentioned beforehand. So let's have a quick look at how I would store a specific pub. In this case, I'm storing a pub as a point. So we have this underscore default, which is my unique identifier. Then I have ty, stands for type, which is either 1 for a point or 2 for a way or polygon. L is the location, and the location has two fields in here: the type, what type of GeoJSON object it is, and then the coordinates. And for a point, you only have one set of coordinates. But it's important that you realize that we do longitude, latitude. So it's x, y. So not what you usually see on maps, you do latitude, longitude. No, there's longitude, latitude. And if you get this wrong, you won't find your documents. So you need to think about this correctly. At some point in the future, we will also get a z-axis. So you get longitude and latitude, I always mix up. So there's longitude, latitude, and then also elevation, for example. Is also something you can store in GeoJSON, but at the moment, MongoDB doesn't support that quite yet. So that's a GeoJSON object, and then the bottom thing is where I have tags, which I've shortened to TS, which in hindsight was a bad idea because people think that's the timestamp, but it doesn't particularly matter. Yeah, and that is how I have the pub to Taiwan, which is unfortunately no longer there. It is now a building site as of a few months ago. So this is how you store points. Now, a line string is how you describe a way. So in this case, there's a road around Trafalgar Square called Trafalgar Square, and there the data type gets a little bit more complicated, right? Because in the L field now, we still have the type around the coordinates. The type is now a line string, but the coordinates is now an array of nodes, or an array of location points. In this case, 4 of them. And this then describes a road or a line segment of anything. And as you can see here, somebody has mapped that a sidewalk. There's a sidewalk on the left-hand side of the road. Why? I don't know. People like doing that kind of things. And then the third object is a polygon. And a polygon is the same thing as a way, except that it is a closed loop. So OpenStreetMap itself doesn't, in its data model, make a distinction between a way and a polygon. But in GeoJSON, you do need to do that. And in GeoJSON requires you that in any polygon, the first and the last element in the array are the same location. So in this case, you can see there's 4 points in the pub, right? But there's 5 points in the coordinates because the first and the last one have to be the same. GeoJSON also gives you restrictions on the shapes of polygons. So you can't have polygons that are self-intersecting. So you cannot define a polygon that starts with this point here, goes to this one here, then this one, and that one. That is not a valid polygon because it intersects on itself. But you can see there's now 3 nested array levels, right? So you have this loop here, which has a starting point and ending point. But you have another possibility of creating more loops in here as well, which you can use to exclude specific things from a polygon. So you have this outer ring, which you specify first, and then you have inner rings that exclude the information that you specify in that inner ring from the outer ring. So you get polygons with holes, basically, so that is used for. So those are the 3 main data types that we can store. And in MongoDB, you can index on this L field, and if you set a specific 2D sphere index in it, you get a geospatial index on that, instead of a normal equality match or a text search match, for example. Right, so a geospatial index works very differently from a normal index, right? In a normal index, well, what you do is you order them according to the alphabet or something like that, right? So you have a list from A to Z, and you put your documents in the order. If it's numbers, the order of your index is going to be according to number. But for a geospatial index, that's a very difficult thing to do because, of course, you have an X and a Y system, right? And you need to be able to match objects in an index. But an object isn't a simple number or a simple string in a long list of strings. It is now geospatial. So you need to come up with a different way of doing indexes for this. So what MongoDB uses, it uses a system by Google called S2. No idea what it stands for. But what it does is it maps the surface of the Earth to cells. And a cell is basically a square, although it is never a real square as you think that if you have a square on the ground kind of thing. Because the Earth isn't a square or a cube, so you need to do something cleverer there than just mapping that. And that is what S2 does. It projects the globe onto the 6 sides of a cube, and then it maps coordinates according to an interesting algorithm, which I won't be able to explain right now because I don't remember it, up onto the sphere, and that is how it indexes it. And the way how it works is that if you have a large object, you don't want that large object to be covered by lots of these cells because that makes your index very large. So there's an optimization in there that in most cases makes sure that only 8 cells cover a specific object. But if, for example, if you have the Netherlands as an index object, then of course that is very different for storing that as, for example, a pub, which is a really small area, right? So the way how it maps those cells is according to levels. And level 0 is one side of the cube, and in level 1, it is then a quarter of that specific face. And every level you increase, you get 4 times as many different cells in there. So the algorithm makes sure that it defines that in such a way that every object matches to at least 1 cell, and at most whatever, in this case, the MongoDB developers have decided, which I think is something between 8 and 16, depending on some rules that I can't remember. All right, so let's just have a look at how that looks like when we look at this. So a point, the toilet's in the top left, you can hardly see the red square here. The point maps to this specific single cell. So if you do an index search on find me all the toilets, for example, on Trafalgar Square, because it knows the size of Trafalgar Square, it can then map the indexes that map all the points in Trafalgar Square with the polygon that you give. So yeah, for example, the road around Trafalgar Square, it isn't all the same cells, right? It's not all the same cell sizes because there's a maximum number of cells that cover it. So in this case, the road covers all those cells with 3 different sizes. Or if you have a polygon, there can be bigger blocks and smaller blocks and so on. Just to make sure that the index themselves, the index entries for each element aren't very, very big. And then what the index algorithm does is if you give it a polygon of Trafalgar Square, and it can then match that with all the different objects on there, like the toilets, for example. So that's sort of how that works. Now, just to have a look at the data itself back again. So if you want to download all of the OpenStreetMap data, you can download that in a bzip2 compressed XML file, which is the last time I updated this slide was 54 gigabytes. I think it is now 70 odd gigabytes. It's a lot of data. Do not, under any attempt, try to decompress this, because you are going to run out of disk space very quickly. I have never tried, so I don't actually know what the size is anymore. Luckily, you don't have to import all of the planet's data at the same time, because you need a little bit more than the laptop. But a country is about doable. Like the United Kingdom is all right for importing on a laptop. I tried doing Amsterdam as well. In Amsterdam, the download file for just Amsterdam is 170 megabytes, which is, even on conference Wi-Fi, downloadable in about a minute. At least it was yesterday. And yeah, those metro extracts, city extracts you can get from the site done by Mapsan, which just gives you the area of a single site. If you do anything with this data, please start with something small and don't try to import the whole world first, because you're not going to have a good time on doing this. So just a recollection, those are the data items that are part of these XML files that you download. And if you uncompress them, you see things like this. The annoying thing is, as I mentioned before, is that if you look at just the ways, they don't have the coordinates in there of these ways, right? They are part of the nodes. Also, in these XML files, you get all the nodes first, then you get all the ways. So in order to efficiently process this, you sort of need to make two loops through the data. So the first one, the first loop that you do through the whole XML file, is that every single time you see a reference to a node, you store the ID of the node and then the longitude-latitude pair. And I'm storing this in a different cache database because I can have this locally, and when I update my website, I don't have to, for this cache database, go back and forward over the network, because that takes a lot of time, of course. If a specific node has any tags associated with it, I'm also storing them in my normal collection. So if a pub is mapped as a point, I'm also storing that in my points of interest collection, and not only in the node cache. The node cache is really only there for the next step, when I look at all the ways, to make sure that I can do a very quick lookup for those nodes that are referenced by each way, to then construct a geometry, the GeoJSON LineString, to then store in my collection of the points of interest. Now, just to have a bit of an overview of what the data sizes for that are after parsing them, and this is, I believe, only storing the pubs, the bars, and the restaurants. Either from London, so when the node cache is about 45 megabytes, and the points of interest collection is 84. Whereas if you look at Miami, this is a very different thing, right? Because it's such a large area, but fewer things were mapped in Miami. You see that the node cache itself is 4 times as large, but the amount of information that directly made use of it is only a quarter of in there. Now, Amsterdam, or the Netherlands, is specifically has a much even higher discrepancy between that, because people have imported all the parks and all the buildings, and that is into a great detail, which makes the maps look really nice, but it does mean that the data sizes are significantly larger. And in this case, if I'm only interested in the points of interest, I sort of have to throw this stuff away, which is kind of annoying, but so it goes. All right, so after we've imported this stuff, we of course need to find things in the database, right? We want to find all the closest pubs, for example. And there's different operators that you can use, and those are Geo Operators. So you remember the specific expression that I used with exists equal true to find all the documents where there was a field text.highway? In a similar way, there's an operator called GeoNear. And GeoNear is an operation that finds things near points. GeoWithin finds things within a polygon or a circle. And geolntersects finds things that are intersecting with other things or are fully enclosed with it. An example makes this much easier. All right, so an example with Near or GeoNear here. And of course, let's hope my demo actually works. Fingers crossed. Yes, it's a bit slow, but there we go. So we are here in the Rai, and what this query does, it finds me the pubs where the tags matches pub, amenity equals pub, and we're finding that near, and then you specify 2 different arguments to near. You specify the geometry. In this case, it's a point with coordinates. So the GeoNear operator only supports points, but you still need to specify the whole GeoJSON document. And it also tells you the maximum distance. If you don't do the maximum distance, you will at most get 101 documents back. unless you specify those yourself. In this case, I don't want to find pubs that are too far away because I'm lazy, don't want to walk on the way there. Right? And then, yeah, you get output here. And you can see that there's no pubs really close by, but there's one called Luce, I guess. But there's a few located here. So if I zoom in, you see all the different pubs that are right here on the corner, and then they're easy to find. Like I said, the detail is very, very detailed in OpenStreetMap, right? You see all the house numbers and heights and stuff like that. It's pretty good. So there's 5 pubs here. So now we have found them, right? And the data that you get back out of that is, of course, something that you see on the left-hand side here, where you have the point and the coordinates. This is in London, not in Amsterdam, but that doesn't matter. And yeah, that's how the data then looks like. So this is a very simple query to find things near something. And a similar thing is you can do with polygons. So, for example, Hyde Park. Well, I want to find all the pubs in Hyde Park. Now, there are no pubs in Hyde Park. There's only cafes. So I changed the query a little bit. So what I've done here is actually done the query in 2 steps. So what I do in the first one is I find the object called Hyde Park, being done in JavaScript here. So I'm looking for, in the points of interest collection, I find one document where the tags match both name equals Hyde Park and where it has a tag leisure equals park. If you don't do the leisure equals park, then you also get all the bus stops called Hyde Park, which is not what we were looking forward to. So the return from this, the first Hyde Park object, looks something like this, right? You have the ID number, the type, and then you have this L field that says it's a polygon, and then it has this array of coordinates which doesn't fit on the slide anymore. It used to fit the other day. Anyway, I'm not sure what happened there. And then, of course, you have the tag, so there's access to it. Yeah, it's a leisure park, it has a Wikipedia entry and has a name and so on and so on. And then, with this new object that I found, I'm then using a GeoWithin query to find in the geometry that we found in the first query, and we're using this L field here, which is this polygon here, and then finding all the places where they are marked as a cafe. So you get the pavilion here, the Lido, the triangle, the boathouse, and so on and so on, to find all the objects within Hyde Park. So if you want to find all the objects in Hyde Park, and this is a bit of a zoomed in stuff here, so the outer line is actually Hyde Park, but that's a quiz question for later. Which park is this? You see that there's some paths in here, right? So the paths here, this bit from here, is found because it's highlighted as blue, well, purple, I guess. But there's other paths here that are not highlighted, and the reason for that is because they actually go slightly outside of the park and connect up with the road. So GeoWithin wouldn't find that because this path isn't fully enclosed within the outer polygon. And to find also these objects, you need to use geolntersects, and then it does that too. So I did that a little bit further away along the street, really. So I have this building here, and I wanted to find all the things in there, but I also found those lines that looked really strange because they are not roads and they seem to be going underground. Which in the end ended up that some person actually mapped the tube lines, including all the platforms underground, and that shows why it shows these lines, right? Yeah, the things you find sometimes. And actually, if you look at the data, they actually have mapped that which line goes under which other line and stuff like that. So there's lots of weird stuff in here. Yeah, what can I say? Lots of special interest people in OpenStreetMap. So in this case, yeah, geoIntersects finds all the things that also cross the specific objects. That's kind of handy as well. All right, so there's a few other things and a few other queries that you can do, because the thing with the normal query operator in MongoDB is that you can only find the documents that it has found exactly as they are in the database. But sometimes you might want to do a few other things. So there's an alternative query system in MongoDB called the Aggregation framework, which is the way how you usually do aggregations instead of a relational database group by clause or kind of thing. But it has an interesting geospatial operator called GeoNear that allows you to also modify documents as they come out of the database. And you can use this, for example, to add the distance between the point that you're looking for as well as the object as an extra field to the document that comes out of the database, which is kind of a nice thing to do. It is important that if you use this aggregation query operator, it needs to be the first one in the pipeline. And what I mean by pipeline is is the following. The aggregation framework allows you to run multiple operations after each other. It is very similar to having like a Unix command line thing where you have pipes in between, right? You do a PSAX to find all the processes, then you do a grab, a match, to make sure that it only matches Apache, for example, and then you do a head -1 to find the top process, right? So those 3 stages can also be represented through the aggregation framework. But the way how geospatial indexes work, you can have GeoNear only as the first one in this pipeline. Otherwise, it's going to be way too slow to use, basically. And the way how this looks like is as follows, right? So instead of using the find method, now I'm using the aggregation method. An aggregation method accepts an array of operations. So in this case, this array here ends down here, and we have one operation, which is this bit here. That's the only operation that I have in this pipeline. And it's called GeoNear. And GeoNear accepts multiple arguments here. So it has near which GeoJSON document you're trying to find things near. And in this case, you can specify more than just a point. You can also specify a polygon or a way. So it is a little bit cleverer than just a GeoNear you have in a normal find query. So we specify the coordinates here in this bit. Then we have the query. So this says basically find only the documents that are either a pub, a bar, or a restaurant. That's the query bit of it here. And then we do some sorry, where did I go? I missed the transition here. Nope. Let's hijack my... Okay. I have to wait because it has to load things out of the database. And now, of course, I went too fast. You know how that goes. Wait. Okay. Sorry, demos are being slow today. There we go. So yes, the coordinates, the query, and when you zoom over that, actually you can see that it works as well. So if you go closer to Takara, I don't know what it sounds like, a restaurant kind of thing. It actually shows you the distance from the red dot, which is the middle of the map, to oh, people have been adding lots of data here, as you can see. So much data you can't actually see what it does anymore. And of course, yeah, you get like the distance as an extra fieldback, so which is kind of handy to find out how far it is to the closest restaurant or pub or bar in this case, which is useful to know. So that's what I had about to talk about. Are there any queries? See what I did there? Okay, if you don't have any queries, I have queries. So yeah, go ahead. Are the geospatial operations much faster than doing your own, trying to find distance with trigonometry kind of things? It is significantly faster than that because it's an index it's an index lookup, right? And the index isn't as fast as you'd have a normal string or number-based index, but it is a lot faster than scanning through your whole database and calculate the distance yourself for every single document or record that comes out of a collection, right? When I imported Amsterdam, I ended up importing 12 million nodes and about 1 or 2 million different ways in the database. And if you, for all of them, have to calculate exactly how far they're from the point that you're specifying, it's going to be a lot longer, right? I mean, it's just CPU time. It's not something that a database can optimize for instantly. But of course, if you have it as an index type, then yeah, that works much faster. And similarly, PostGIS has something very similar to this that is also optimized for this kind of queries. So yeah, it's definitely faster. All right, anything else? Yeah, go ahead.
Yeah, so is this something you would use in production or just for fooling around or research?
I use it in production. I think, well, there is a Scottish mapping, not Scottish, I think the Scottish Land Registry also uses it for their geospatial stuff. Not for the standard things where they keep all their official records in, but as a public viewable thing, they use that. If you've ever used Foursquare, the geospatial lookup on that is based on MongoDB's geospatial support as well. So yeah, it's definitely used in production, and I would use this for most web-related projects. If you do heavy like GIS kind of things, you'd be better off using PostGIS for that because it has so many more features than that. But for lookups and finding things near things or intersecting with stuff, this works really well, and I think it is a lot easier to use than PostGIS. That's personal opinion, but yeah. I would definitely, if I have a geospatial project, I would definitely not discard this instantly as a toy kind of thing, if that makes sense. Yeah?
Are you able to import this data from OpenStreetMap just for a single polygon?
Can you import just from a specific polygon? So my little import script doesn't do that. But what you can do is download from any of the sites that I mentioned a few slides earlier, a specific area. And there's tools that can operate on OpenStreetMap data that can cut out specific polygons. So if you get the rectangles from the site, apply this extra operation on it to cut out, for example, only a neighborhood or the city area, and then you get to import that. So there's tools around that.
It will be a lot faster.
Sure, that'd be a lot faster. Yeah, the smaller area you have, the faster it goes, right? Yeah, that's true. Anything else? Yeah, one there.
Yeah, maybe it's a bit hard to explain, but if I have two ways, which are not exactly the same, but they are the same street,
Yeah.
can I also find a way to find the intersection of those two?
You will be able to find the intersection of those two ways if they exist, but if they're just slightly parallel, you're going to find it very difficult to find that, right? There is no operator at the moment that says, find me everything not more than 5 meters from this way, for example. That at the moment doesn't exist. The distance limitations at the moment are only to specific points, although it is on our list of things we want to implement at some point. But yeah, the intersection of two ways it will still find, as far as I know. Yeah. Anything else? No? Very good. Anybody recognize which park it was? Oh, which park was it?
St. James's Park.
That is correct. You win absolutely nothing. But yes. Yes. Anyway, that's what I had to talk about. If you have any further questions, feel free to find me at the conference later. I'll be around for a while. Please leave feedback at Joined In. Yeah, that's everything. Thanks very much. Yeah.